Hi everyone, thank you so much for joining us for Enabling Rust for UEFI Firmware webinar as part of the UEFI 2020 Virtual Plug Fest. We're going to give it a few more moments for people to log on and then we'll go ahead and get started. Thank you. All right, let's go ahead and get started. So as I mentioned before, thank you again for joining us for Enabling Rust for UEFI Firmware webinar. I'd like to take a moment to introduce you to our presenters. So we have Jiwen Yao, who is a principal engineer in the Intel Architecture, Graphics, and Software Group. And then we have Vincent Zimmer, who is a senior principal engineer in the Intel Architecture, Graphics, and Software Group. And I'm going to go ahead and pass it off to them.
Hey, thanks, Megan. So yeah, thanks everyone for calling in this morning. And what Jiwen and I are going to talk about this morning is give a quick overview of EDK II security, and then dive into the Rust language, follow it up with how to enable Rust with EDK II, and then we're going to tie off with a summary and call to action. So this is how we're going to regale you this morning with information. And to begin, I'm going to provide, again, a quick overview of EDK II security summary. So this is kind of the obligatory slide you'll see in a lot of security-oriented talks. This is an infographic recalling some high-profile attacks against host firmware in the last few years. But the audience here is probably pretty aware of these issues in the market. And in fact, UEFI Forum hosted, I think, a really nice talk yesterday on attacks and the need to do updates from inside an Eclipsium. So really, we look at this talk as complementary to that talk. You know, we believe updates are imperative to remediate issues in the field. But what we want to explore today is, you know, perhaps tactics to employ when creating code, such that, you know, maybe we can catch some classes of these issues at development time. So that's sort of, again, we're composing next to yesterday's talk. And to motivate our talk, we really want to provide some observed data. So this chart is derived from the open source TNO Core advisory. We have this the TNO Core EDK II TAs, and it provides some classification of the issues. It really creates the top issue classes. And the top scoring issues relate to memory safety and integer overflow, namely buffer overflows and misuse of integers. And these are, if you look at our metric, about half of our open source issues. We derive similar numbers from some of our closed source code, but you'll see that the open source has more of this initial issue class. And we sort of see that because EDK II the open source has a lot of complex algorithm-intensive flows. A full network stack, file system drivers, the capsule processing. And if you look at these sort of thick stacks algorithms, they consume a lot of attacker-controlled data, tricky data manipulation that may come from third parties. And a lot of these issues prevail because EDK II is predominantly written in C. It's maybe, 95%, 98% ANSI C, and then the rest is a little bit of assembly code. And you can sort of think of C as a portable assembly language, the weak type system. It's hugely flexible and expressive. The guys at Bell Labs invented it in 1972 to write the original version of Unix. But some of the challenges of the language are it expects the developer to, quote, get it right, meaning, and I guess one of the analogies I heard once that I liked is they compare programming in C to smoking a cigarette while standing in a swimming pool of gasoline. You can do it, but you have to be awfully careful. So is this, though, an issue of just for the host firmware? Well, we're citing this material from Microsoft that shows that it really isn't just the EDK II project that observes this large class of defects based on memory safety. In fact, Microsoft has, when they looked at their vulnerabilities, about 70% are seen in of our memory safety issues seen in their C, C++ code. Just as I said, thicker software stacks, more algorithmic intensive, you have more opportunities for this class of flaws. And so as we observed 50%, Microsoft is in fact citing 70%. So we don't believe this class of concern is just for the host firmware. We think it's more pervasive for essentially writing software in C. And in fact, to that end, we really see firmware as just really a class of software. The definition of firmware, I think I looked it up. What do people call firmware these days? Is, quote, software stored in a read-only device. As we know, there's not so much immutable firmware these days. A lot of the firmware is field updatable. It's co-designed with hardware, so that's maybe a little different than generic, software. But in reality, we see the act of firmware production, maintenance, and assurance is really akin to other class of system software construction. It's really software. And you really have to worry about the same maladies that afflict software: buffer overflow, integer overflows, and uninitialized variables. This is a concern of all classes of this critical software. And regrettably, buffer smashing, buffer overflows were first observed by the Multicians in the Multics report in the 50s, and it's still, quite prominent as a vulnerability class. And so, we've sort of motivated our talk here was to explore with the industry some software techniques that perhaps can help address these concerns. We see the number, we see 50%, Microsoft sees 70%. Firmware is really software. And so that's kind of why we wanted to bring this topic in today. We don't think there's a silver bullet, though. In fact, there's sort of a tiered or 3 levels of approach to getting rid of vulnerabilities, to addressing vulnerabilities. The first is, eliminate the vulnerability. Can you, as the old saying goes, it's much cheaper to fix a bug in development versus having a patch in the field. Both are important, but from an economic standpoint, if you can catch the bug while you're writing it, it saves time, effort, and perhaps cost versus having to roll an update and work it through the supply chain and your customer base. So on the prevention side, eliminating the vulnerability, we actually have a large class of capabilities today are already in hand. You know, system management mode has been a popular attack vector. So we have the profiling mechanism, so you can look at what SMM handlers you have and perhaps remove some. You know, there's open source and closed static analyzers, sanitizers. A community-introduced host-based firmware analyzer, which can really use things like American Fuzzy Lop and other fuzzers. And we have checker tools like ChipSec. So did you program the registers? If you saw our vulnerability classes earlier, there were a few of them on register locking. So we have a clutch of capabilities for eliminating the vulnerability. The next step is, okay, the vulnerabilities got out there, but can you break an exploit? So if someone gets in, do you have some defenses in place? Just as we said, firmware is really software. A lot of these classes of defenses are employed by broader system software and operating systems. These include things like stack canaries. Can you leave a little bit of information on the stack to detect if it's been overwritten? Randomizing your address space to make it harder for attackers to have a targeted attack, and then making your data allocations non-executable, and then your code area non-writable. You know, again, these are a class of capabilities that are employed today in operating systems that we can bring into the firmware and have either deployed or examples of. And then there's also emergent defenses like control flow guard. There's some compiler work there in addition to hardware such as Intel CET we've enabled in system management mode. And then finally, ones that are pretty familiar to folks are things like UEFI secure boot, signing your updates, namely check the code integrity. Did the code come from a unknown entity? And again, a lot of these defenses are in place or prototyped. Some of them we haven't deployed end-to-end because of things like application compatibility. You know, trying to do the no execute with an EFI app will take some work with the app community to evolve that. But we have quite a bit of these protections to break the exploits out. And then finally, the third level of prevention is containment. Unlike the former two where we have a lot more examples, these are kind of more emergent. And again, it's really here to erect code, walls around the code to inoculate the system from maybe bad behavior. And this can include deprivileging through software like inline reference monitors with our EFI bytecode, hardware rings, or other isolation technology. So, you know, this is an area I think is a potential to explore more. But, you know, one of the questions we asked today is this all we can do? You know, are these the class of preventions, exploit, defenses, and containment, or is there something else? And we believe, you know, these three levels of protection are still eminently important in the examples we showed, but perhaps there's a more pervasive approach to that first level of prevention class, namely eliminating the vulnerability that we mentioned in the last slide. And that maybe, you know, approach can be, you know, how we write the code. And to that end, you know, can we have a programming language that provides us stronger type safety to eliminate some of these memory safety issues, but at the same time don't sacrifice, you know, the execution efficiency and expressibility we have with C as a flexible, you know, as a systems programming language. So we think, again, you know, exploring a different language is a complementary elimination approach. And to help answer that question, can a language be applied in this area? We're going to introduce the Rust programming language and its potential applicability to firmware programming. And to provide more details on Rust itself and how we might get there, I'm going to hand off to Jiwon at this point.
Okay, thank you, Vincent. Now let me introduce the second part of this presentation, which is have a brief introduction for the Rust language. So, Rust is a new system programming language. It was designed by Mozilla Grandin Hall and was first released as at 2014. The most attractive attribute of Rust is its reliability. It has rich type system and the ownership mode to guarantee the memory safety and thread safety. The persistent programming language is used to write the operating system and device drivers. With that, the C language is the most popular one. However, C is also notorious for the memory safety issue. For a long time, people believe it is hard to write a secure code with C. We know the buffer overflow for more than 30 years since Morris Worm, but today we still see the buffer overflow issues exist in the firmware. Among of this type-safe language, Rust is not the only one. Compared with others, it is very fast and memory efficient because the memory issues are eliminated at the compile time instead of runtime. Unlike other type-safe language, some of the language, the Rust does not have the garbage collection. As such, it can provide some performance-critical services and run on the embedded system. Besides the language attribute, Rust has a good community and a great document. The Rust compiler can not only detect error, and it also teach you how to fix the problem. Rust Clippy is a static analysis tool which includes a collection of links to catch common mistakes and improve your code. Rust embeds a unit test framework. It supports developers to write unit test cases along with the code. Other security tool like AFL has a Rust version. It allows the developer to run AFL++ on the Rust code. Last but not least important, Rust considers the interoperability with other language. For example, you can let a C language to call, you can write a C function to call a Rust function, or to let a Rust function call a C function. Currently, we have already seen some Rust-based projects, such as Amazon Firecracker, which is a micro-hypervisor. It's a Facebook library. It is a blockchain digital currency. There's a Baidu Rust SGX SDK for the secure enclave, and the Redux OS, which is the operating system written in Rust. We're also seeing some firmware projects like All-Boot firmware. It is based upon Coreboot but without C. Here we'll introduce some basic concept of the safety attribute in Rust, which might help the EDK II developer to have the basic understanding of what Rust can offer from security perspective. The gist of the Rust memory safety is to rule out the mutation in the presence of aliency. There are three patterns for data moving. The first one is called ownership. If the ownership of an object is passed from one function A to a function B, then the function B owns the object. Then the function can read or write this object. When the function A, the original owner, can no longer access this object. The second pattern for data moving is called shared borrow. If the object's immutable reference is passed from function A to function B, then the function B can only read this object, but it cannot write or update this object. And the function A can still refer to the original object. To be clear, in Rust, any data type is considered as immutable unless it is explicit state as mutable. The third category of pattern named mutable borrow If the object's mutable reference is passed from function A to function B, then the function B can update it. And the function A cannot cannot update this object during the borrow time, for example, in a for loop. But the function A can update this object again after the loan is returned. For example, after function call returns from B or outside of the loop. So we want to summarize the memory safety issues in BIOS we have observed based upon the threat model. The most critical one is the buffer overflow on write, which impacts the integrity of the BIOS, such as UEFI secure boot, flash update, or SMM. The confidentiality is not very popular because the password is an optional feature. We have seen the setup password or OPPO password or HDD password. Some of them are stored in SMM. However, if there's some buffer overflow issue, it may cause some information leak in SMM or cause the password exposed. Other pointer issues such as use after free or double free, we do not see a real case so far in EDK II BIOS. Risk condition may happen inside of the SMM when both AP and BSP trying to access some memory, but it's also very rare in the EDK II system. Uninitialized variable may bring some unpredictable problem or hard to reproduce issue. I remember that we have some experience that a random TPM failure problem just because policy data was not initialized correctly. The initialized value was from stack randomly. We always got different results in different build and different machine configuration, and it took us almost 1 month to nail down this problem. All this is caused by uninitialized policy data. Memory leak is out of scope of memory safety issue. It is availability, and the memory leak is not resolved by Rust. Now, Rust uses different ways to resolve the different problems. For buffer overflow issue, the best way is to load the object and refer it based upon the defined data structure. So the out-of-boundary access can be detected at compile time. However, the reality is that we might also need to use offset or index to access a slice of this buffer, especially for the complicated data structure. Then the Rust compiler injects some code to do the runtime boundary check. If the out-of-boundary access is detected, the code called a panic handler. Then the panic handler can be implemented as a dead loop in EDK II, which is similar to the exception handler. The worst case is that there's some vulnerability, but it can be broken by this exception, by this panic handler. The heap issue, such as use after free or double free, can be managed by Rust ownership model. The violation will be detected at compile time. Also, the initialized variable is automatically eliminated because Rust explicitly requires the initialization. Null pointer dereference is an interesting question. The inventor Tony Hall treats the null pointer as a $1 million mistake. It was invented in 1965 just because it was easy to implement. Eventually, it has led to innumerable errors, vulnerabilities, and system crashes. If the data might be no value, we should use the option T in num for this data structure. And the program can use some T pattern to get the data and use the null pattern to handle the no value case. Non-pointer dereference may also happen in memory allocation failure. The Rust uses alloc error handler for the allocation check at runtime. If we believe that the memory allocation should always be success in this pre-boot phase, then we can use a dead loop in the alloc arrow handle, just in case someone trying to break the system and cause null pointer dereference, it will be caught by this dead loop, and the exploitation is broken. Besides the memory safety, the arithmetic error contributes a large portion of root cause of the overflow, such as the integer overflow on addition or multiplication. Some famous spikes issue, such as BMP overflow in 2009, was caused by multiplication overflow. And EFI capsule coalesce issue in 2014 is also caused by addition overflow. Rust provides a flexible way to handle that. It defines a set of functions such as checked add, overflowing add, saturating add, or wrapping add. Besides those functions, Rust has a compiler flag on overflow check for the direct operation. Named the -c overflow check equals on or off, we can indicate if this runtime check is needed or not needed. If we indicate this runtime overflow check, the runtime check will run into a panic handler if the runtime overflow check fails. If the compiler flag is not used, then the default behavior is the debug version will generate the checked code, while the release version just discards the overflow data. From our perspective, the Rust check version function is similar to the existing safe_int_lib in EDK II. The developer should choose the right version to pass the external input. If the external input is not trusted, we probably need to use the checked add or checked multiplication to detect any error there. Typecast is another risk. Rust always requires the explicit typecast at compile time, so this risk is also eliminated automatically. Rust also defines a different type of pointer. The raw pointer is similar to the pointer in C language. Unfortunately, it is unsafe. Rust cannot guarantee the memory safety for the raw pointer. No compile time check for it. It should only be used for the interaction with C functions. The reference pointer is to point the memory owned by some other value. The Rust can guarantee the memory safety for the reference. It is preferred to a raw pointer. The reference can be pointed shared in mutable memory or exclusive mutable memory. The developer must explicitly indicate the mutable type for the reference pointer. In Rust language, all values are allocated in stack by default. If we need to allocate some data in heap, then the box pointer can be used. A box is a smart pointer to a heap allocated value with value type. The allocation happens when the box type is created automatically. When the box goes out of scope, its destructor is called. The inner object in Rust is destroyed and the memory on heap is freed automatically. So it can free the developer side. With box, the developer doesn't need to write allocate free functions. What you need to do is just define a box type and use it, and that's all. All we have discussed before has a Rust memory safety guarantee enforced at compile time, except the raw pointer. But there are some other features in Rust which cannot enforce the memory safety guarantee. This is called Unsafe Rust. It works just as a regular Rust, but it gives us some extra superpower. The first untrusted code is dereference a raw pointer. So it cannot guarantee the point to a valid memory, and the Rust cannot guarantee it's just not null. It could be null, or Rust cannot implement automatically clean up for the raw pointer, which is different with the reference. The second category named the core unsafe function. Unsafe function means has some extra unsafe keyword before the rest of the definitions. The unsafe keyword in this context indicates that the developer need to guarantee the safety, because Rust cannot guarantee that we have meet all those memory safety requirements. For example, calling an external C function is an unsafe behavior. We need to use the unsafe keyword. The third unsafe code is to access the Rust mutable global static variable. Rust does support global variable, but the global variable can be problematic with Rust ownership rules. Think of this case: if two threads are accessing the same mutable global variable, it may cause a data race. The fourth category is named implementing a Rust unsafe trait. A trait means a collection of methods defined for unknown type self. A trait is unsafe when at least one of its methods has some variant that the compiler cannot verify. If a trait is unsafe, then the implementation may be unsafe. The last unsafe code is access Rust union. A Rust union is similar to a structure, but it's only one declared field in use in a particular instance at one time. Union is primarily used to interact with the union data structure in C language. Accessing union field is unsafe because Rust cannot guarantee that type of data is currently being stored in the union instance. In that case, for the unsafe code with that means the developer tells the Rust, please trust me and I will handle that. With those introduction of Rust, we jump to the third part of this talk, how to enable Rust in EDK II. So we created the EDK II Rust branch in the EDK II staging repository. We you can build a EFI Rust module with the Rust cargo execute in Windows or Linux. In order to generate .EFI image directly, we may use x86 underscore 64 unknown UEFI target or i686 unknown UEFI target. Both of them are available in Rust language Git master. These targets are also used to generate the PCOF library in Windows or Linux. To build the Rust library and the C library together, we can use LLVM9 compiler, which is also supported in EDK II at this moment. The EDK II base tool is updated to support different build type. So you can indicate a .rs file in an .inf file. You can create a cargo.toml file and add to INF. And you can link a Rust library with a C driver, or you can link a C library with a Rust module. It's very flexible. Rust, we create some basic example of Rust in EDK II. For example, fat Rust is a simple read-only fat file system library. It can read a OS loader from the UEFI system partition and boot to it. Rust version EFI libcrate provides the memory allocation, debug log, and the EFI boot services, etc. We noticed that Rust language only supports UTF-8 style native string, but the UEFI requires char16 Unicode string. In order to fill the gap, we create EFI string crate to handle the char16 string for the UEFI developer to write to help them to write the code easily. Besides that, we also did some research for a pure Rust version crypto library. Currently, Rust TLS is a modern TLS library with Rust. It uses ring as a cryptograph and a web PKI for the certificate verification. So we try to enable ring and web PKI in EFI bare metal environment as a Rust version crypto library. Unfortunately, the ring and web PKI kit does not support UEFI target very well, so we create some dedicated branch to add the UEFI target OS in their code. And another thing we noticed that the ring and web PKI use the C standard library rand. In EDK II, we do not have a standard library rand function. We have our own base lib or base memory lib, etc. As such, we created the EFI random crate to use the read rand instruction or read seed instruction to link with ring web PKI crypto library to support randomization functions. Besides our investigation, we noticed that some other EFI Rust projects in the open source GitHub. For example, REFI provides the reference definition for UEFI services and protocols according to the UEFI spec. The only unfortunate thing is that the definition is not complete. It just defines the most common used EFI data structure for OS boot. EFI-RS provides a wrapper for writing EFI application, and the Redux OS includes a wrapper for UEFI services. Rust hypervisor firmware is a simple virtual firmware with a minimal UEFI support. It reuses some of the REFI definition, and it can boot to the to Ubuntu OS loader and boot to the operating system kernel. And Microsoft demonstrated the Rust-based unit test in EDK II. They provide a Rust-based EFI library solutions, EFI variable policies with a unit test. With all this benefits we see for Rust, we also see some limitations. So Rust language can guarantee the memory safety. There are some limitations for using Rust in the EFI environment. First, the UEFI specification and the interfaces, such as EFI boot services or protocols, are defined in C language. So in order to operate with other modules, we need to use a C-style API. That means unsafe code is always required. It is unavoidable. So we may convert. So currently, most EDK II has a written in C, and it is hard to convert all EDK II code into Rust at one time. We may convert part of module into Rust, but still use other module in C. But we do see there are some area Rust can help. Here's a summary. First, to eliminate the vulnerability, we can use the compile time check. For example, we can eliminate the uninitialized variable, the unused after free, double free can be avoided by the ownership model. Second, we can break the exploitations. The Rust can help to generate runtime check for the memory boundary check or integer overflow check. In case that the developer cannot write code correctly, the violation can be caught at the runtime. It may cause a dead loop. But in order to avoid the dead loop, the developer needs to write the correct boundary check code and use proper integer operation functions. There are some other areas Rust cannot help. For example, there are some vulnerabilities that the silicon register does not lock correctly, but Rust language does not understand the secret register lock attribute. We might need to use a chipsec tool to check if all required registers are locked properly. Security policy means to enable or disable some security feature such as UEFI secure boot or flash lock or SMN lock. So it is not related to Rust language. We need a policy checker there. TOC/TOU attack is something happens in SMI handler. We have a software pattern in SMI handler design. For example, we need to copy the SMN communication buffer into SMN RAM and then check it, then use it. And we may also need to rendezvous all APs in SMM before the SMI handler to unlock some critical register. They are also out of the language scope. A careful security design review is required to eliminate those risks. The SMN callout issue also requires a hardware restriction such as SMN code check SMI set or non-executable bit in SMN page table. The last portion is the unsafe code block in Rust for C language interaction. The unsafe block always need a careful code review. Please be aware that putting some code in Rust unsafe block does not help from the security perspective. We notice there's a project called C2 Rust. It can translate C into Rust directly. However, it is unsafe Rust. We still need a developer to refactor the Rust code and turn them into a native Rust language and get the benefit on memory safety issue. With all those introductions, we want to call for the actions. So we notice that 50% of EDK II security issues are caused by memory safety, and the Rust is a good language that can help mitigate the memory safety issues. However, to rewrite the whole EDK II might be hard, but we can start convert the most critical firmware modules into Rust and get benefit on the memory safety. And here is a link we referred in our talk. And to learn more about the EFI security, I would like to focus that Vincent and I has written a book named Building Secure Firmware. We will share our knowledge and thought on a different perspective of firmware security. So it will be available on Amazon soon. So that's all our talk. We can move to the Q&A section. Any questions?
Oh. Thank you. The first question is, do you believe all EDK II can and should be rewritten in Rust?
I can answer this question. I think it will be yes and no. From technical perspective, it is possible, but it will be a huge effort to port all EDK II modules into Rust. So when Rust is introduced, it does consider that compatibility issue. So Rust resolve it by use FFI, which stands for the Foreign Function Interface. So you can call Rust from C language and call C language from Rust, with informed risk that there's no safe guarantee if you just call out to a C function. But it does provide some flexibility to allow people to move C code to Rust step by step. For example, you can port the most critical part in EDK II to Rust and keep use the rest in C and make it stable and release it. When you have time, you can port the next one, make it stable and release it. Then you port the next one. It doesn't need to be port all EDK II into Rust. And from security perspective, people want to get benefit from porting to Rust. For example, memory safety is a primary reason we move from C to Rust. So if porting can bring some huge benefit. For example, a module has suffered from a module have many security issues, that could be the high priority to want to port. But if some code just register programming, we never seen security issues there before, and then the benefit might be small, and it could be a low priority. It's like a trade-off between how many resources you have and how many benefit we can get from it.
Right, and that kind of incremental approach is something you observe with even the Mozilla community. They've been porting part of the browser, the renderer, servo to Rust, but the most of their code base is C, C++. I think the Chrome browser is pursuing a similar approach. Given the large investment in the existing working code and the nice interlanguage interoperability of Rust, it gives you the opportunity to just, port, those critical areas where there's maybe assurance concerns. You treat attacker control data, but you're not necessarily driven to rebasing your whole code base in the language. We think that's a valuable aspect of Rust also.
The next question, are there any plans to add Rust capabilities into the PI portions of EDK II?
So, Vincent, do you want to?
Yeah, sure. So yeah, if you think a lot of the packages described today, the PI DXII is our UEFI implementation. So our focus here isn't the third-party application creation having, there seems to be already community support for them to move their applications into Rust. Really, the capabilities we've been talking about here are some PI capabilities. So, for example, some of the DXII implementations. But also some of the PEI code would be a good candidate. So like capsule coalesce, for example, it's very tricky logic. Critical C flows like that in PEI could get ported. Some of the libraries G1 shared as prototypes. So yeah, we think this effort is really about assurance of your UEFI implementation. So critical areas and DXII and PEI. And is where we would address. So, but the same caveat that, not the whole code base, but critical points in the whole boot flow where there's maybe some assurance concerns through PEI and DXII. So yes, that's our approach. Now, if the question is, are we going to upstream, if we're going to upstream these tools and it's going to become part of master, there's no timeline for that, but from a technical perspective, definitely the whole PI stack is a potential candidate. Sorry, Megan, go ahead.
Sorry about that. Is the future strategy of EDK II to move C code UEFI to Rust?
I think we want to provide that option to the community to explore. There's again, there's a big caveat around this. I was in D.C. at the airport waiting to fly back to Seattle, and I was behind David Grawrock, or not David Oxsmith, excuse me, Hawk, and I asked him his thoughts on using, safe languages for, addressing some of our firmware concerns. And if you know Oxsmith, he's a pretty tall guy, and I'm not so tall, so he sort of peered down at me and said, "Hey, Vincent, if that's such a great idea, why haven't you all been programming in Ada for the past decade, right? The core boot community has an Ada binding. I don't see so much Ada work going on." So, we don't think a safe language is a silver bullet, but really what we wanted to do was engage the community and show that it's feasible and show maybe some of the business value. But, moving to EDK II, I think would be something we'd want to hear from the community and the industry. Is it makes sense because it's not just these technical merits, is it can we still have developer productivity, debuggability, maintainability? There's a lot of aspects of curating a code base. So we don't have a defined strategy. I think what Jiwon and I really wanted to do is open the possibility engagement with the community, and because I think there's a lot of parties whose consideration reads in on moving to a new language.
Yeah, the primary reason we share our idea is that we did some investigation. We heard people talk about Rust for a long time, and we heard people say that Rust is such a good thing, why we just adopt it. But we also need to think about the productivity and what the benefit we can get. So we realize that Rust can bring some benefit, but we also need to realize that Rust is not a silver bullet, like Vincent mentioned. We still have some other vulnerability we need to consider. So all in all, we also need to think about the productivity. So if Rust, if some EDK II code has external interface and it pass the complicated data structure, and we are suffer from fixing security issues there, that could be a good candidate. We report those modules. But if there are some other feature which does not have any security assurance required, just do some register programming to initialize the silicon, that could be a low priority thing.
Right, and just like we import OpenSSL and treat it as a black box or the Brotli compression code, maybe if there's some of this code which is more invariant of platforms, class-like code or generic code, that if it's ported and people don't typically touch anyway, but it's demonstrated vulnerabilities in the past, maybe those are good candidates, versus, as Jiwon said, things that just bang registers and you'd have to, put unsafe decorations around it anyway, or, it doesn't take third-party input, maybe just leave it alone, the present coding idioms we have. So yeah, we're pretty open-minded, and we want to, again, temper technology advantages with some of the real business reality of maintaining a code base that's used through a broad, diffuse supply chain.
Next question, what is your opinion about other boot firmware projects written in written, such as Google's Rust-based ORBoot, which is core boot without C?
I'll go with my 2 cents, and then Jiwon I can only do 2 cents. He probably has $1 worth of feedback, but my 2 cents is, it's a clean room project, starting from scratch, ground up. If you're starting, Ron Minnick, when, I chatted with him about Rust, and he's the core boot, ORBoot, on point. He said, it's almost immoral that you start, quote unquote, start a new project in the year 2020 and not write it in a safe language. So I think maybe that project has the luxury of being a greenfield project, and, they've really constrained the scope. So I think greenfield constrained usages, I think it's great. OpenTitan, how using the Taco OS, a platform root of trust, the constrained microcontroller usage, greenfield project again. I'm a fan. Use the best tool for the mission, and they have the liberty that these are green space projects to start with Rust.
Yeah, I heard the same opinion. Besides ORBoot, that OpenTitan Vincent mentioned, there are also some other projects like the Rust hypervisor firmware, which is also a firmware, but it runs in the guest environment, guest VM environment. It's very simple. It's just load the load the OS loader and jump to the entry point and the peak of image. So it should be very simple. It can be loaded by a Rust hypervisor. So that is a good candidate for written Rust directly.
Next question, Are you receiving any help from the community and UEFI forum members in evolving firmware to Rust?
Yeah, I think it's Jiwon noted the example of Microsoft doing the unit tests, and I think is a great example. I think they did a branch off the staging tree, and yeah, so I think efforts like that, more engagement, more usages, I think is part of the reason I think we showed up today is raise awareness, and then all the artifacts we pointed at are public. Love to have more community engagement and feedback on the approach and priorities and feasibility of some of this. So yeah, definitely that's part of our mission today is to spread awareness to have more community engagement.
Yeah, the committee is very important. One good indicator for a language is that how many libraries available for use directly. So if a developer wants to do something and want to reuse the existing library, that would be easy for him or her to finish his job or her job. That can increase the productivity. But if there's no much existing library, he need to write every line of code from beginning. That is hard. I think that's also that is always a challenge for the new language, and I think Rust also run into this situation. If we can see the community can help and provide more and more Rust-based library then we can use that library to build our modules. When we have more modules, then they can. So only after we have more modules we can replace the EDK II code with Rust one by one. So definitely we want to community to look at this Rust and provide their thought, feedback, or write some libraries to help us on this.
Great. Well, thank you, Vincent and Jiwon so much, and thank you all for attending the UEFI 2020 Virtual Plugfest presentation. As a note, the presentation slides will be available on the UEFI Forum website, and a video recording of this presentation will be available on both Bright Talks and the UEFI Forum YouTube channel. Thank you all so much.
Hey, thanks everyone. Really appreciate the questions and your attendance.
Okay, thank you.